today I want to talk about our work, multi-user CDH problems, and the concrete security of HMQB and Nexus. And this is joint work with Eike Kiltz, Shashin Pan, Magnus Ringerud. So as you might have guessed, this session is about key agreement. So if you haven't known, HMQB and Nexus are two key exchange protocols. And an authenticated key exchange protocol is a very fundamental cryptographic building block. It's widely used in applications. Each time you connect to a website using the TLS protocol, or each time you initiate a chat using Signal or WhatsApp, a key exchange protocol is run. And from a cryptographic perspective, the goal of these protocols is to let two parties compute a shared session key while at the same time authenticating each other. So we will use public key primitives to exchange the key, and then we can use the more efficient symmetric key primitives to encrypt further data. And so in this setting, we will look at interactive protocols between two parties. So consider here Alice and Bob, who both have long-term keys consisting of a secret key, SKA and SKB, and a public key. And we assume that public keys are known to the other parties, and then these two parties will exchange messages. So we're looking at interactive protocols. And at the end of the interaction, they should both compute a shared session key. And they should also know who they are talking to. So this is the authenticity property in these protocols. And I'm interested in the security and the provable security of these protocols. So what we usually do, we look at game-based security notions. And on a high level, this means that the session key of the two parties should not be distinguishable from a uniformly random key. And before I go into more detail with this, I will first recap how we prove security in general and what it has to do with the concrete security. Okay, so we prove security by a reduction. That means we assume that exists an adversary A, which is attacking our protocol in this predefined security game. And from this adversary, we construct a reduction that tries to solve some underlying computationally hard problem. So the reduction gets a problem instance, and then it somehow embeds this instance in the interaction with the adversary. And if the adversary wins the game, then the reduction should be able to extract the solution to the problem. Now, but if this problem is indeed computationally hard, then such an adversary cannot exist and our protocol must be secure. And now we want to quantify the success probabilities of these two instances. So let's say the advantage of the adversary in winning this security game is denoted by epsilon A, and it runs in time TA. And the advantage of the reduction in solving the computationally hard problem is epsilon B, and it runs in time TB. And we now say that the reduction is tied if these values are about the same, because only then we know that the protocol can be only as secure as the underlying problem is hard. So we would always aim for tight security where this is indeed the case. And this is in particular important for key exchange protocols, which you will see when I go into more details about the security of these protocols. Okay, so we want to define security in a game. And in this game, we always want to model the reality as close as possible. So indeed, we don't want to look at this two-party setting, which I showed you before, but each user in the system might do a key exchange, might access a website. So we're looking at n users, and they all have their key pairs, and they all can have their own sessions. So let's assume there are in total S sessions, and we associate a secret state to each session. This could be, for example, the randomness that is chosen by the party to generate the next message. And now we want to give the adversary complete control over the network. And we do so by giving it oracle access to the network. So via the send oracle, we let the adversary choose which parties should interact and which messages they should send. So in particular, it can modify, inject, or even drop messages. And then we also want to give it access to secret information. So it can be that users are compromised, secret keys are lost or stolen, and we model this with a corruption oracle, which the adversary can query, and then it can get the secret key of this party, and it will, of course, be able to impersonate that party like in the future. And in some sense, we still want security if some of these corruptions happen. We do the same for the secret state of a session. So the adversary can query this reveal state oracle to get access to the state and even to the session key. And in this case, it should get the real session key. And now we haven't talked about security yet, so we add an additional oracle, which is a test or a challenge oracle. And this basically models what I said before, this key indistinguishability property. So we have this bit here, which is chosen by the game. And depending on this bit, the adversary will either get the real key, this is now for user C and E, or a random key. And the goal of the adversary is to guess this bit. So and if the bit output by the adversary, B prime, equals B, then we say it has won the game. Now, when we prove security, the reduction has to simulate this whole security game. And this already looks complex with all these oracles and these many users. So actually, we can see that by having all these secret information, the reduction must be able to simulate all of this. The oracles can be queried adaptively, so the reduction has to know all the secret keys, session states, and also session keys. But it also has to embed the problem instance. So we run into a problem here, because how should it know which users are corrupted, which session keys are queried? And the user strategy we follow here is we would just focus on one session only. So we guess one session at the beginning of the game, and then we prove security only for this. So let's say we have guessed this session here, and we would embed our problem instance in this session. And now we can make some case distinctions, and then construct our reduction, and it will succeed if the adversary really decides to attack this session. But of course, this is not a good strategy, because so for many AKE proofs which use this strategy, they will have a huge security loss. So we don't have this epsilon A is about the same as epsilon B, but we will have this factor of S squared here, which we call the tightness loss. And if S gets really large, like 2 to the 30 or something, what does it mean for concrete security? Maybe we don't have any security or theoretical security left. And in order to compensate for that, we would have to increase the system parameters of our crypto. So for example, we could choose larger elliptic curves or larger RSA moduli. And this is something which is not done in practice because it comes with a huge efficiency penalty. So the question is, can we get rid of this tightness loss? Can we maybe give a tight proof in the first place? And it turns out that for many protocols, it is shown that this is impossible, at least constructing reductions to standard assumptions. And the protocols I want to talk about, HMQB and Nexus, they are indeed subject to these impossibility results. But the question is, can we still make some statements about the concrete security of these protocols? Okay, so first let me show you how the protocols work. So these protocols are defined over prime order groups. So G is a generator here, and the secret keys of the parties are scalars in ZP. And the public keys are the corresponding group elements. Okay, now to start the key exchange, each party would choose a random scalar, and then also compute a group element and send it over to the other party. And they would also compute some additional values that depend on these messages and on their own identities. It's just to bind the identities to the key. And then they compute this expression here, which looks a bit complicated, but it would just mix like the secret values known to each party with the public values of the other party. And then in order to derive the final key, we would hash everything together. So G is a hash function here, I haven't mentioned that, and H is just another hash function, which is used to derive the key. Okay, and well, you can compute this term, and you will see that both parties indeed compute the same key, so correctness holds for this protocol. So this is the HMQB protocol. The H stands for hashed, and the MQB protocol was indeed proposed for some IEEE standard in the early 2000s, but there was no security proof for that, and this hashed variant is secure, but so far people only have looked at the asymptotic security. Okay, the Nexus protocol follows a similar structure. We would just now not choose X and Y directly, but we would first choose a random bit string of some length n, which is linear in the security parameter, and then use a hash function to derive that value. Okay, this is also referred to as the Nexus trick, which will let us prove security against the state reveals. Because as you see here, the input to the hash function is also the long-term secret key. So here at this point, we mix long-term secrets with ephemeral secrets, which gives us stronger security. And then in order to derive the final key, we will now compute 3 Diffie-Hellman shares. So we will use the public key and the public keys of both parties, mixing them with the ephemeral keys, and compute these 3 values. Okay, so these are the 2 protocols. I will now focus on the HMQB protocol only, and I want to highlight a few things. So here's the protocol again. The one thing I said earlier, the reduction must know the secret keys of users in order to answer corrupt queries. But if you look at this protocol, the public key of L is G to the A uniquely defines the secret key. So the reduction has to decide, okay, do I know the secret key or do I embed the challenge? And this is what we call the commitment problem. And we have the same for answering the key reveal versus test queries because we don't know which of the 2 will happen. And this is also where all these impossibility results come from. So when something is uniquely defined, you don't have a chance to avoid this guessing strategy. So what can we do? So we restrict the class of adversaries, and in particular, we look at the generic group model. So in this model, we take the group, which underlies the protocol, and we only give the adversary access to the group structure via oracles. So for each group computation the adversary wants to make, it has to query the oracle, and now we can define the complexity of an attack in terms of the number of oracle queries, and this gives us information theoretic lower bounds for these generic attackers. And when we instantiate the protocol over elliptic curve groups, these actually match the best attacks we know. So this is a stronger model, but all attacks that we know today actually only exploit the group structure. And then what we do is we capture the algebraic core of this protocol. So instead of looking at this 2-user setting, we would see we define multi-user versions of this problem, and then this will simplify the proof because we can just direct prove it without this guessing and without case distinctions. And then we provide the generic group bounds in order to justify the concrete security of the protocols. Okay, I will show you how our assumption looks like. So if you're familiar with the computational Diffie-Hellman assumption, you will see that this is not much different. So instead of 2 group elements, we look at, as the name says, multi-user. So we look at Q instances of the problem. So the challenger would just choose Q scalars at random and then send the corresponding group elements to the adversary. And now the adversary can decide which Diffie-Hellman share it wants to compute. So it has to output a group element Z such that there exists indices I and J such that Z is the Diffie-Hellman share. Okay, now we have defined a multi-user version of this, but we also want to model corruptions. So before outputting the solution, we give the adversary access to this corruption oracle, and it can adaptively decide which secrets it wants to see. And then, of course, the solution cannot use one of these corrupted values. Okay, and additionally, we will need a gap-like assumption. This means that we have a decision oracle, which I denote by DDH here, where the adversary can just provide any 3 group elements, and then the challenger will tell it whether this was a valid DDH tuple or not. Okay, this is just for some technical details in the proof. Okay, and we denote this assumption by the Q core gap CDH assumption, and we show that this tightly implies the security of the Nexus protocol. For HMQV, we need to add an additional oracle because we have these identity binding steps there with the additional random oracle. So we add this challenge response oracle because it has like this challenge response style. K is just the index, so the adversary can query this oracle multiple times on group elements, and it will just receive a random value. And then we show that it has to compute this value Z here, which somehow looks like the Z value in the HMQV protocol. And we show that this tightly implies the security of this protocol. Okay, I want to briefly say how the proof works. It's basically pretty straightforward, so with this assumption. So we will have to parameterize the assumption by the number of users and the number of sessions. Here's the protocol again. So we show that HMQV is a tightly secure key exchange protocol under this assumption, and we will use the random oracle model to idealize the hash function. And then the idea is pretty simple. So the reduction gets us input. I now labeled these values as the first n will be the AI values, and the next s will be xj values. So we will embed or use the AIs as the user's public keys. We will use the xj's as the messages which are sent back and forth. And then you remember that we had this corruption oracle, so now we can easily just forward these corruption queries to our corruption oracle in the assumption. And we can do the same for the state reveal queries. Then I said it before, we need this DDH oracle to somehow patch or to handle the key reveal queries. So, and in particular, we need to maintain consistency between the random oracle queries and the key reveal queries. And this is where we will use this decision and oracle. Okay, and then, for the G values, we will use this challenge response oracle. It turns out that if now A queries the random oracle H on the correct value of this value Z of the protocol, then this is directly a solution to the protocol we had, to the problem we had. So we have shown that if the adversary manages to break the HMQV protocol, then we can use this to solve the assumption I just told you. If this was too abstract, now I give you a few numbers. What does that mean for concrete security? So now we divide the running time of the adversary into offline and online computation. So you can think of the offline time as, since we're in the generic group model, as the group operations, because this is usually something the adversary can just do offline. And the random oracle queries, because we idealize a hash function here, this is also something that we want to happen offline. So this offline time is usually much larger than the online time. Online time, on the other hand, is the number of users and sessions, because for this, the adversary has to interact with the system, and this is usually much smaller. So, and I put the optimal GGM bound here. This is what I said for elliptic curves. This is the time we would need to break D-log. So this is like this baby step, giant step approach to break D-log, and this is the optimal bound, which we would like to have for our protocol as well. Let me show you the old bounds. So this is what previous work had. And I want to highlight like the difference to the optimal bound. So we have the square root here in the denominator, which comes from applying the forking lemma, and this is extremely bad. But you also have this online term here, and the same for Naxos. So this is very far away from the optimal bound. And with our analysis, we now get rid of the multiplicative terms, and we only have this additive term here. And now if this is still too abstract for you, let me talk about bit security. So we always want to target, let's say, 128-bit security, and we can express this as dividing the advantage of the adversary with the running time. So if we plug in usual parameters like elliptic curves of size 2 to the 256, and the offline time we set quite large, and the online time a bit smaller, then actually we don't have any security left for these old bounds. But our work now shows that we really get the desired security level when we restrict us to generic attacks. And this is quite nice, because now we also have the theoretical confidence in these protocols. Okay, to conclude, so we proved the tight security of HMQB and Naxos based on our new assumptions, and then we analyzed these assumptions in the generic group model. And the consequence is that we do not have to increase the system parameters if we want to deploy these protocols in a theoretically sound way, but we can just rely on this analysis and do the thing we always did, use standard parameters, and this is still theoretically sound. Okay, that's it. Thank you for your attention, and I would like to answer questions.
I'll ask a question. Thanks for the talk. There's another model called the algebraic group model, which is slightly weaker than the generic group model. I'm wondering if you considered that model and whether you think similar bounds could hold in that model.
Yeah, we were actually looking at this afterwards. So we didn't prove anything yet, but we have some confidence that we can reduce to other assumptions that were used before, and then we would just get the same thing, yeah. But this was just simpler to analyze it. Oh.
So my name is Marian Škrvot. I'm a research scientist at University of Luxembourg. So although it sounds fancy, it's just the postdoc with a temporary contract. So today I'll be talking about wireless channel key exchange, and this is a joint work with my colleagues Afonso Arriaga, who is present here, and also Petra Schall. Okay, so yesterday at this room there was a panel that discussed the migration strategies to post-quantum world, and basically in realm of key exchange, I think it was panelists mostly agreed that we should do hybrids when transitioning to post-quantum world. And there's a so I wanted to explain you what was the motivation for this work. So, and there's a nice paper by Dowling, Hansen, and Patterson, where they combine the classical AX, post-quantum AX, and a quantum key distribution protocol, and they provide a framework and show how to run hybrid key exchange and combine the key outputs from all these three paradigms. And then I was wondering, is there something else to add? Is there some other type of key exchange that can be added? And just very few days after that, I stumbled upon a paper that was explaining physical layer security. I don't know how many of you have heard about this concept, physical layer security. Yeah. So very few people. So I was also surprised. So the main idea there is that physical layer security techniques exploit the physical properties of communication channels to provide information theoretic security guarantees. However, it's only against the eavesdropper. So there are two approaches, two groups of techniques that are applied in this physical layer security, and those are keyless approach, where some kind of physical layer encryption is used on a physical layer already to hide the messages in the transport. And then there's the other keyed approach where the keys are extracted from the physical layer and then used later on the higher level network layer. And you may wonder, okay, this is only secure against eavesdropper adversary. Why we go for this? So there's maybe potentially we can add a layer of protection on the physical layer at low cost. And why I say at low cost? I'm saying this because most of these techniques use existing hardware. So the wireless antennas that we already have. So you can think of the small sensors maybe that have wireless antennas, but they do not have a setup, a secure setup, so they could use these kind of techniques. And we'll be looking into the keyed approach here. Okay, so let's look at specifically the key exchange. So in literature, there's hundreds of papers, and I think mostly they're published on still communication venues. So mostly signal processing community was looking into this. And they have very different names for the same primitive, so we wanted to make give a catchy name. So we proposed wireless channel key exchange, or WIKE. And the idea, this is the idea in WIKE. So you have two wireless-enabled devices that can send probes to each other in the first phase, and then later, obtain random sequences, correlated random sequences, and then they can run over the authenticated public key channel. They can run kind of error correction to agree on the secret keys. So this sounds quite a lot like a QKD, at least later stages. And we have a Eve that's present and can make the measurements like the two other parties. Okay, so how this works? So why this is secure? Why this can this be secure? So there are three assumptions that are that needs to be fulfilled. First of all, we need to have some kind of channel variations. They need to be present, either temporal, spectral, and/or spatial. And in other words, it means that we need a good source of randomness at first. So for crypto to work, we need a randomness. The second thing we need that has to be fulfilled is a channel reciprocity. This means that that the channel is identical in case we have a channel between the initiator and transmitter is identical, even if we flip the roles of their roles and they do the measurements in the same time coherence period and the same frequencies. And this is typically satisfied in this wireless environment. And finally, there's the third one is a security critical one, spatial channel decorrelation, which says that the adversary also can make measurements and he obtains these random sequences, but in case he's apart from the legitimate, the measurement, the measurement devices from the legitimate parties, the random sequence that he obtains will be somewhat decorrelated from the measurements of the legitimate parties. And hence, in practice, when we speak about the wireless communication on 2.4 gigahertz, this translates to 6 centimeters. So meaning that the adversary, if it's further apart 6 centimeters from the legitimate parties, will receive, his measurements will be uncorrelated to the legitimate parties. Okay, so how the WIKE design looks like. So I'm not sure if this is if all the WIKE proposals capture this, because there's hundreds of them in literature. But from what I've seen, most of them follow this. So there's a first phase, which is advantage creation phase, and this happens on a wireless channel. So first we have probing, then the legitimate parties try to extract the channel features, and finally there's a quantum channel quantization to transform this analog signals into the digital random strings. And then we run information reconciliation phase, which is basically error correction, and which is followed by private simplification. And so now we'll see why. So after the advantage creation phase, the Alice and Bob will have correlated signals, and Eve will have, because it's further away from the legitimate parties, you'll have the computed value will be somewhat more decorrelated. And then we run information reconciliation phase, and as a result, now Eve and Bob will have the same bit strings. However, there will be some bits that will be leaked to the Eve, and therefore we need to apply. So this now is not cryptographic distributable key. So now we need to run private simplification, which will compress these strings into a now key that's outside of Eve's knowledge. Okay, so when we were checking all these papers, we were surprised that there is no security model. So there are some security measures or notions, but not really the key exchange security model. And then we wanted to see, okay, well, can we propose one? And we decided to go for a game-based model. So Doreen previously really nicely explained the key exchange model. So yes, so I won't be going here into details. It's already explained. How there are some differences. In our model, we don't have state reveal. The problem is that the authenticated channel assumption basically is saying that the adversary sees all the communication. So the long-term secret is used only to achieve integrity of the messages at the time that the bike is run. So there's no mix between the long-term secret and ephemeral values. So we cannot achieve security. We cannot prove security in this model. So we have only the reveal of the session key query. And on top, we need to add a probe query to model this advantage creation. And let's now zoom in. So this models the first phase of WIKE, and then send query is modeling the second. We model the second and third phase of WIKE protocol. Okay, so let's zoom in into the probe query. Now we'll have a joint probability distribution that will model the environment, and then we'll have a realization of the random variable x, y, and z bit strings that are sampled according to this probability distribution. And here, the bit string z will be given to Eve, while x and y will be kept private. So this is different than normal key exchange protocols, because in normal key exchange protocols, we assume that everyone has the same view over the transcript. And this is different, hence, so the execute query won't be as always. Okay, now when we model security is the same as in standard key exchange protocols. And the security guarantee that we want, that the session keys are indistinguishable from uniformly and independently sampled random keys. Okay, and so I mentioned already, we need a good source of randomness for this to work. And one problem is that sometimes in some environments, this is not fulfilled. So depending on the WIKE method that we use, depending on whether the communication happens indoor or outdoor, is it line of sight communication, whether the nodes are moving, or what is the distance between the sender and receiver, we can have different key rates. And from the literature, we gathered that this secret key rate ranges between 0.5 to 15 bits per second. And this translates to 15 seconds to 8 minutes for 256-bit key. Maybe if you want 128, you can halve these values. But I guess for most of the application, this seems like too much. So if you want some kind of a quick communication between mobile phones or some other devices. So one So then we pose the question, how to quickly establish a section key in case of slow key generation. And one potential solution is to use password authenticated key exchange. So my background is in password key exchange, so you know how they say if you hold a hammer, everything that you see is a nail. So this is how we see it as well. So how this works, so it's possible that, so you imagine you run a WIKE protocol, and your protocol realizes that some threshold time has passed, and there's not enough bits for secret keys. So then we can run PAKE to bootstrap this low entropy secret into a high entropy session key. So so now we wanted to see what are the minimum, what is the minimal assumption over PAKE, so that we can compose it with a WIKE that's secure in our model. Okay, and let me just go back. So now thinking about the security, the question is like, do we want to save this low entropy value somewhere and keep it as long term? And the answer, I would say is no, because once you run this PAKE once, you can just continue using this key from first session. It does happen. So we are not saving this low bit string for further sessions. And this will, then we provide a game-based model for the whole composition. So here we have again probe query to model the first phase of WIKE. We have send query to model the second and third phase of WIKE and the whole PAKE. The reveal now reveals the PAKE output, because this is the session key. Corrupt leaks the long-term secret from the WIKE setup. And then the test query it models semantic security. So the difference with the Doreen model is that here we assume that the adversary can ask multiple test queries. That's why it's a real random model. And this helps with also in a PAKE and WIKE. And this helps with the reduction, so it's easier. You can do in one swoop, you can exchange all the keys in the reduction proof. Okay, and so there's few observations we can make that. So the real random secure WIKE produces the keys that are indistinguishable from truly random keys. And then usually the drawback of the real random security model in PAKEs is that it cannot properly model correlated passwords. Because in real random PAKE, game-based PAKE, the passwords are selected uniformly and independently at random, which is not the case in the real world. However, here it's really the case. So then this real random PAKE, we don't need to go for UC in order to compose these protocols. And of course, the composition will inherit all the limitations from WIKE and PAKE. So basically, we'll have this non-negligible bound here. So this is number of attempts over the size of the dictionary. And the dictionary K depends on the threshold that the WIKE protocol accepts. So if we have, it can be 30 bits, for example, and so this will be the 2 to the 30 size of the dictionary. So, and because the strategy the adversary has is just to skip the WIKE part at all and then try to guess the password that goes into PAKE. So that's why we definitely have this bound. And then we show that we can, in a black box way, compose these two protocols and obtain the bounds that we want. One thing to note, we don't need, because of the choice that we are not saving this low entropy value coming out of PAKE, we don't need forward secure PAKE. So so if you assume that we are not saving the output of WIKE, we can just use non-forward secure PAKE. Okay. And also we have, in our paper, we also have the analysis of previous attempts to do this. And we found some issues with in the proof. And also, interestingly, we found an attack that was introduced because the authors, they removed the server identities from some kind of confirmation codes. And this led to an attack that usually does not appear in PAKES. It's even really hard to capture. In real random model, it's hard to capture. So basically, if this protocol would be used in a normal PAKE setting, the adversary would be able, just by interleaving the messages, would be able to test whether the client uses the same password across multiple servers. So that would be easy to do. And then it has practical consequences that if one server is easier to compromise, so they could go for easy compromise and then attack the other server. Okay. So to conclude, we proposed a game-based definition for WIKE. We provide a generic solution for slow key rate problem in WIKEs using real random PAKEs, and we've kind of studied what are the minimum requirements over PAKE. And then we show also that there are security issues in previous attempts to compose WIKE and PAKE. So one thing that we realized once we've written the paper is that now it was much easier to kind of see, okay, what can be done for WIKE now? Can this be improved? Because the people from signal processing community, they were focusing on working on this first phase of the WIKE and not looking into second and third phase. So they were taking this from QKD protocol. So there are several maybe potential ideas. So it's maybe possible to drop the authenticated channel assumption and to use information theoretic secure authentic key agreement from Dodis et al. So we still need to look into that. So it depends. So that they've shown that if the best bit string, the secret key is n. So if there's n halves of bits that are not known to the adversary, then their technique works even in and the adversary does not possess the knowledge of the final key. The second also possibility is to skip the third step, the privacy amplification, because now to use, instead of normal PAKE, to use the UC secure PAKE. UC secure PAKE admits correlated passwords and also if some of the bits are leaked. So this would also potentially work. And finally, we could also run only the first phase of WIKE, obtain these correlated dirty random secrecies, so that which are close but not exactly the same. And then we could use a fuzzy PAKE construction to compute the keys. So these are the open questions, but I think I know opens nicely. So what can be done, and to maybe leverage some extra information that you have depending on the distribution of the random sequences once from the first phase. So, and with that, I close. Thank you. So do you have some questions?
Oh yeah, could you go back to slide 12 real quick?
Yes.
Whoops, wasn't slide 12. Yep, that one.
That one, yeah.
If by some mischance Eve were to not have any errors, so here it's basically a random string, no trace of what Alice is sending is left. But if it just is exactly what Alice sent, would that be a fail state?
Yeah.
Okay.
Yes.
And so,
Yes.
I guess
So
how do you ensure that? Do you have some mechanism for ensuring that Bob and Alice are sufficiently far apart that whatever correction you have is going to just barely correct what Bob is likely to get? So if Eve is any further away, it will be almost certainly unreadable? Or do you have anything like that?
So, yeah, so the point is you could use the thing. So you could use, because you have a kind of high entropy authentication. So you could use some other stuff, but we want here to achieve information theoretic security. So then I guess, So I think there are these boundaries, the results from Dodis on fuzzy extractors, on what are the, how many bits needs to be, how big advantage from Alice and Bob needs to be in order to run, to eventually end up with the secure keys.
Thank you. That
So
makes
and I
sense.
think that the bound is, I think what they have is half of the, so if you have 128-bit key, the half of it has to be unknown to the adversary.
Okay, and in that case, so if Alice and Bob were close to each other, it could potentially have low entropy communications, and they would do something like adding entropy into the communications just to make sure that Bob would be at the limit.
Yeah, that's possible as well.
Okay,
yeah,
makes sense.
yeah,
Thank you.
yeah. Okay, thanks.